Now we're going to learn about LeChatelier's principle. When you have a system whose equilibrium is disrupted, it will shift in a way so as to reestablish the equilibrium. It'll shift to the product side or to the reagent side to get back to equilibrium. So write the mass action expression for the reaction of 2HI forming H2 and I2. Pause it, try it, and you should have come up with product concentrations in the numerator and reagent concentrations squared, because the coefficient is 2 in the denominator, equals Q, and in this case you're at equilibrium, so that equals KEQ. Now, if we take this system at equilibrium and we inject iodine gas into the system, all right, so we add iodine to this system. Now, at the instant that we add the iodine and before equilibrium is reestablished, is this Q ratio going to be greater or smaller than KEC, than the equilibrium constant? Of course, with the numerator growing, because you've injected iodine gas, Q now becomes larger than KEQ. So the system is no longer at equilibrium. And what has to happen to the concentrations of HI, H2, and I2 if Q is to change to once again equal KEC? In other words, to reestablish equilibrium. And of course, it has to shift away from the products toward the reagent side. The amount of H2 and I2 decrease, and the amount of HI increases, and that lowers the value of this ratio until Q equals KEQ. So still considering the same system of hydrogen iodide decomposing to hydrogen and iodine. Using the same logic as we did in the previous question, describe what has to happen to the concentrations of HI, H2, and I2 if Q is to change to once again equal KEQ, if the following changes are made to the system at equilibrium. So, the system's at equilibrium, Q equals K, then we add hydrogen iodide gas. In what way is the system going to shift? Well, if we add hydrogen iodide at that instant, the ratio here, the denominator increases in value. That means the value of the ratio decreases, Q decreases, and becomes smaller than the equilibrium constant. So the system has to diminish the amount of HI, it has to grow the amount of hydrogen and iodine, and the system will shift to the product side. What about hydrogen gas being removed from the system at equilibrium? What's that going to do? If we remove hydrogen gas, the numerator decreases in value, Q decreases in value, and to make up for that, the system has to shift toward the product side to increase the value of the ratio so that Q increases to once again equal KEQ. And what happens if hydrogen iodide gas is removed from the system? Let's say you have a chemical in there that absorbs hydrogen iodide or something. What effect is that going to have? This ratio becomes larger, Q becomes larger than K, and the system has to shift to make Q smaller by shifting toward the reagent side. So if we remove HI, the system shifts to make more HI and will consume hydrogen and iodine until the value of Q equals KEQ. Now, as it turns out, temperature can be a factor that influences the position of equilibrium. Consider this equilibrium, and we're given that it's an exothermic reaction. The enthalpy of the reaction is negative 33.6 kilojoules per mole. So if you thought of heat as a thing where you could add it to the reaction would heat be on the reagent side or would heat be on the product side for this equilibrium? And of course, if it's exothermic with a negative delta H, heat is going to be released, therefore we can think of heat as a product. Now, if the reaction was heated, how would the equilibrium shift? Reagent side toward the product side. Well, remember B is our equilibrium including heat as a product. And if we raise the temperature, if we add heat, we're going to drive the equilibrium toward the reagent side. Now, the thing is, heat is energy, it's not concentration, and it's not part of the mass action equation. But rather, its addition changes the value of the equilibrium constant. So, for heating the above reaction, where we know that heating it is going to drive the equilibrium toward the reagent side, what effect is that going to have on the equilibrium constant? And of course, if you drive the reaction toward the reagent side, at equilibrium, the Kc at that new equilibrium is going to be a smaller number. The value of Kc is going to decrease compared to what it was at the lower temperature. Now, suppose a reaction is endothermic and it's cooled. Would Kc increase, decrease, or not change? And of course, if you have an endothermic reaction, it's going to look like A over here, and you add heat to it, it drives it to the equilibrium to the product side, and therefore at equilibrium the Kc will be a bigger number. Kc will increase at the higher temperature for an endothermic change. Now for gases, concentrations in the mass action equation can be expressed as molarity or as partial pressure. We use Kc for molarity and Kp for partial pressure. Increasing the pressure of a gaseous system at equilibrium will cause the equilibrium to shift toward the side of fewer gaseous moles. So if you've got this equilibrium, 2HI yields H2 plus I2, and the system is put under pressure, will the reaction shift toward the reagents, products, or not shift? And of course, you have equal gaseous moles on both sides of this. 2 gaseous moles on the reagent side, 2 on the product side, so even putting it under pressure is not going to have an effect on the equilibrium. Okay, let's try this one and pretend the double arrow is a little bit more centered. And let's say that the pressure of the system is lowered. Would the reaction shift to the reagents, products, or not shift? Okay, so you have a total of 7 gaseous moles, 3 and 4, on the reagent side, and 2 and 6, or 8 gaseous moles on the product side. So there are more gaseous moles on the product side than the reagent side. If the pressure of the system is lowered, the system responds by producing more gaseous moles. The production of more gaseous moles is favored. So this reaction would shift toward the product side if we lower the pressure of the system. How would you change the pressure of each of the following by changing the volume of the whole system to increase the yield of products, if this is possible? So on this one, here's calcium carbonate solid, forms calcium oxide solid plus carbon dioxide gas. You have 1 gaseous mole on the product side. So would we decrease volume, increase volume, or is it not possible that volume is going to have anything to do with this? Well, remember, your gas laws, the pressure is influenced by the volume. If you decrease the volume, you increase the pressure. If you increase the volume, you decrease the pressure. So if you wanted to make more gaseous moles, you'd want to shift it toward the product side And therefore, you would want to lower the pressure to force the system to make more gaseous moles, which would happen. So if you increase the volume, you decrease the pressure, the system would respond by producing more gaseous moles. How about this one? Solid sulfur plus 3 fluorine gas yields 1 mole of sulfur hexafluoride gas. And you want to produce more sulfur hexafluoride. So here you have more gaseous moles on the reagent side, and therefore if you increase the pressure by decreasing the volume, you would push the system toward the side with fewer gaseous moles, which would be the product side. And the last one, chlorine gas plus iodine gas forms 2 moles of ICl, and here you have 2 gaseous moles on the product side, 2 gaseous moles on the reagent side, so pressure is not going to have any effect on this equilibrium, nor, of course, is changing the volume.